hopefully you're all looking at question 6. I've made a slight improvement from last time. I noticed a lot of you were staring at your screen like it was a postage stamp diagram, you couldn't read it. So I've enlarged the screen. Does that look better? Is it easier to read what the heck is going on, right? So in this thing here, this table here is the same kind of table as we did last time. And we're going to go through the whole process of creating it. Unfortunately, there's not a shortcut to that because we have to kind of, well, I can skip some of the bits, but not many. So let's look at the first part of the story is that certain kinds of tumours tend to recur. The following data represents a length of time in months for a tumour to recur after chemotherapy. Okay, so 19 months, 20 months, 39 months, and so on. I'm hoping this is when they do reoccur, right, how long it takes. I'm hoping there are a big chunk of people that they kill it and it's gone and you live the rest of your life without it, right? So let's be optimistic. These are for only the people who end up getting, you thought you'd killed it, but darn thing grew back again, right? So we have a whole set of data here, and we're going to break this guy into 5 classes. So I'm going to calculate that thing by taking the big number, take away the small number, and dividing by 5. Now, although you can't see what I'm writing, big take away small divided by 5 groups, right? 5 bins. I can see the smallest number. That was easy, 1. I'm looking at 50. I'm looking at 59 now. Can anybody beat 59? Is that the biggest that's there? If you agree 59, I'm using it. Is it? I'm getting a nod, we're going for it. Right, 59 is the biggest. Subtract 1 is the smallest and divide it by 5. So on my calculator here, I'm going 59 take away 1, which is obviously 58. I'm going to divide it by 5, and I am looking at 11.6. Now, don't you have to round that number off to a nice whole number? And you always have to round up, don't you, just to be safe, right? So that means that I'm now going to do 12. That bit, you can write in, there's the 12, we're done, right? Now, class limit. If I start at, if I start at 1, the smallest number, where do I finish so that there are 12 numbers in that? Okay, 1 to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's got 11 numbers in it. And you might say, but I remember last day you went and said you added 1, right? Well, let's look at that. What's 1 and 12? If you subtract them, that's 11, then you add 1. So count with your fingers. Your fingers are going to be your friend, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see how in this case you get 12? Suppose, sorry.
Also with the last case, we started from 0 and not 1.
Yes, and that makes a difference because you're thinking what I'm about to say here. Suppose the smallest number was 0. Where would we finish now to get 12 numbers? Well, in that case, we would finish at 11. 0, and then count through your fingers. While we're at it, suppose the smallest number was 9, right? It could be 9, right, for whatever reason. Where would you finish to have 12 numbers? You could either do it with your fingers or you could just do a shortcut. Where would you finish if your smallest was 9? What would be the last number?
20.
Agreed. Now, if you subtract those 2, do you see it's 11 and then you add the 1? So, yeah, it's one of those fiddly little things we just have to live with. So you start with 1. No. Yes, and you finish with 12. Agreed? The next group's a little bit easier. Don't you start with 13? In fact, I like to go down the columns here. So the next one's going to be 25. I hope. Yeah. Next one's going to be 12, 37. And the last one's going to be 12, 49. Oops, 49. Does that look good? How do I know these numbers, even though I haven't figured out where it finishes? What was the pattern I was using here?
You just said 12.
You add by
Yeah.
12.
Just, yeah, whatever it is. If it's groups of 12, keep adding 12. Now, on the second side, don't you just do the same thing? Although this is kind of nice because it's multiples of 12, so I'm less likely to screw up here. Now, here's the final check that this is good. Does this group here contain the biggest number?
Yes, the biggest number is 59, and 60
Right.
is bigger than 50.
Exactly, right? If that last group, let's just suppose I screwed up and the last group was 48 to 58, right? If the last number in your last group doesn't contain, right, the biggest number, then you've either screwed up your interval size, right? And I can, if I can, I'll just say it. Can you imagine that 11.6, which we rounded up to 12, can you imagine it was 11.2 for a minute, right? Imagine we did it and it was 11.2. Do you know that still rounds up to 12? You always round up. I say something like you always round up to be safe. If 11.2 was what you got, you still need to have an interval of 12. If you did it to 11, you'd actually be one number short at the end and it wouldn't be a good group. So it's a little fiddly thing, but watch it. Now, class boundaries. Knock off 0.5 and add 0.5. And basically, if you have any number in the range, nothing 0.5 to 12.5, won't it round off to a number between 1 and 12? That's basically what the boundaries are saying. Now, the next group of numbers are really just add 5s each way, so I'm sorry that it's going to take forever, but I need these numbers. It's not that this is difficult, I think it's more just time consuming. There we go. Oh, I didn't mean to do that. Oh, good. We're cool with how that part of the table is created. Everyone's good so far. Right, for the questions I'm about to do, I don't need the midpoint, so I'm going to totally do away with that. I'm not going to do the real frequencies. Well, maybe I could. You're going to do it for me because I'm totally bad at counting. How many numbers are there from 1 up to 12 in this group? And how many in the next group, I'm going to do 40, 90, 60, and you do some of the others. So I'm doing 40, 90, 60.
There's 6 between 1 and 12, it looks like.
Okay, I'm doing 6 in case somebody disagrees later. 1, 2, 3, 4, 5, 6, 7. I'm doing 7 here. Has anybody got any of the other 3 guys?
It's like there's 9 between 13 and 24.
Okay, use that. Someone's got a little comment. Oops, lost it. Okay. Just got 2 more to go. If not, I'll just put in random digits. I just want to show you what you do and to get the next thing. So, you got anything for either of these 2?
I see 4 for 25 to 36.
Okay, I got a 4 on that. And somebody going to tell us the last one?
I believe it's 15.
Oh, right. We'll not double check this. Can we just pretend that it's right? I may tweak one of them. 1, 2, 3, 4, 5, 6, 7, 2, 4. There should be 42 here. 15, 19, 29, 34, 41. Okay, one of these will have to be 5, even if it's not, just so it adds up, right? Now, relative frequency you can calculate. Don't you use 6 divided by 42, 9 divided by 42, 7 divided by 42. Cumulative frequency, 6. What number goes in this second box?
15.
Right. So we're all comfortable with this, and then the next one's 20. And next one's 35. And if everything adds up, shouldn't the last one be 42, right? So that's why I tweaked that one so it would be 42. So you fight your way through, you get all this stuff, things are cool. You then pick one of these histograms and basically you just look at a histogram that has these heights. But I think last time, wasn't it easier to use the start and finish values so you know which one it was? I don't want to do any on that. The guy I want to do is this ugly fella. I've already had 2 different people have problems. How do you do an OGI curve on WebAssign? And how in particular do you do this one? And now I've just realized I need to get my data. So I'm just writing down what the cumulative frequencies are: 6, 15, 20, 35, and 42. And I'm writing down my class boundaries. So I'm writing down the 0, 12.5 one and all the other ones as well. Now we'll show you how it works because it is quite messy. The smallest number is the first boundary. It was 0.5 to 12.5, right? That was the first interval, right? 0.5 to 12.5. At 0.5, which I'm guesstimating is there was nothing. So I'm going to put a dot, whoops, I'm going to go here, pick that, and is that the right table? Yes, it is. 0.5 dot, and then 12.5, it had a height of 6. And boom. Now, there's no way in the world that is very accurate. So if I go up here now and click line segment, do you know I can change this one to now 0.5? And I can change this one to 12.5, comma 6. So do you see that my first shot was really just in the general area of, and then I would go and I tweak it. Because I can't, you could see how, how could you plot that kind of scale, right? Now, the next number after 12.5 was 24.5, right? So I'm going to go up in 12.5's kind of thing until we finish. So I'm going to go here, I'm going to click on this, I'm going to pick, that is my first dot, and 15 at 24.5, which is about here, and I've got my second dot down. And I'll go over to this segment and I'll say 12.5, which is good. That should be 6, nailed it. Second one, that should have said 24.5, so I'll tweak it. But I did get the 15 right, and boom. I'm good. So I'll go over here. Third one, right, I'm going to cheat here. I'm not even going to make an attempt. Right, click here, oops. Well, I can still do it. Here to here. And then I just go back and I fix that one and I make sure that that one there says 15. And I make sure that, this one says, whatever the right number is and so on and so forth. I guess I should put this one in, shouldn't I? And what's the next one? 36.5. And it finishes at 20. Oh, click off there somewhere. There. Can you imagine then that you just nose to tail, nose to tail, nose to tail, and eventually you'll have the whole thing done, and that's the OJ curve. You probably will watch this video very slowly and you'll pause and say, okay, got the first 2 done. pause. Now know how to do the second. Oh yeah, I got it, and you can finish it. But it is very sort of awkward, doesn't it? Just clunky. But it's how we do it. And move on. A whole load of do the same kind of thing. Draw another one. Nothing special here. And now we are going to look at a new guy in town. So that's the question I probably will look at, but let's do ours. Oh, Morgan, who's the babby?
This is Cody.
Hi, Cody. Oh.
Hi. Say hi.
Hi. Hey, Cody, do you know if you stick your tongue out for too long, it sticks that way and you'll never be able to talk again?
Did you know that? He says no.
Does he believe me?
Do you believe him? He says no.
I don't blame him. Can I tell you a story? As you know, we have a huge family. If you don't, I do. And there's lots of quite cool traditions in my family, and one of them was that all my sisters and my brother, whenever their wives had a new baby, you always bring the baby to the house, and my mum loves babies, so she would get it and spoil it to death, and you'd hand the baby to my dad because he's got to hold the baby at least once, and my dad would always hold the baby like this. I don't know what to do it here. It's yours. And we used to do that. And when my sisters had their babies, my mum ended up being the babysitter so they could go out to work. And I think I've told some of you this story before, but I'll share it with the others who haven't heard it. My dad was not much at looking after kids. He thought they were a pain in the butt. So he thought it was fun to just learn them to swear. So the little 3 and 4 year olds would come and my mum would look after them and my dad would learn them to curse. Here's a new word you can learn. Try this one, right? Beep. And it used to drive my sisters crazy because they would come in and, you know, to pick up the baby. And I think the one I'm talking about was called Amy. And Amy would come up and say to her mum, beep, de beep, de beep, 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 mum. And where did you learn all those swear words? And she said, Papa, and which was true. And so the story is that we thought of a way to cure the kid. So Morgan, does your little fella swear?
Definitely not.
Good. If he goes near your grandpa, he may learn to swear?
No.
Okay, well.
Hopefully not.
If he ever picks it up and he's young, this is the cure. What we did is we know that babies, you know, little kids do that because they love the reaction that they get when someone swears. Everybody goes, whoa. And so we decided to do a little trick where we'd get her to change to a new swear word. So we invented a new swear word and it was called MFI. It was MFI. And it's just the 3 letters of a flat pack company that you build furniture with. That's all it was, MFI. But it's a good word because you could go, oh, MFI. And so we had to set it up well, but my sister was in on it and she was there and Amy was playing with her doll and I pretended to get really angry at something in the newspaper and I went, oh, MFI. And Mary, oh, Donald, that terrible swear word. Don't you ever, you know, went the whole routine. And, you know, little ears are, ooh, new word. And so we waited because we knew it would be a little bit of time. And a couple of days later, she was playing with her doll and she got annoyed at something. And she went, MFI. And we were ready. And we did the whole, how dare you, who learned you that swear word? That's terrible. Never use it again. Oh, she loved it. Oh, she's got this swear word. Better than the other ones. I forget the other ones. They don't work. This is the new one. And people would come into the house and she would go up to them and go, MFI. You know, and nobody was ever offended. It was working great for probably about a week because that's all it lasts, these things. And there was a television that was on and an advert came for MFI, the company. And you could see the little brain going, she was pointing at TV and went, MFI. And she figured out it wasn't a swear word anymore. So if you want to do that, you probably should pick a word that's not likely to be seen on TV. So there is a cure for that. Oh, another one, and You know, I got to get these out of my head or my brain doesn't work right. This is true with Amy. I seem to have a lot of stories with Amy. She's a great niece. You know, most people don't like certain things and you can't really know where you've got them. And I've mentioned the theory. You know, you might hate carrots or you might hate potatoes or broccoli or whatever, coffee or something. And there's a great chance that the reason that you hate it is sometime in your life, there's the first time you ever tasted a pickle, right? And there's the first time you ever taste coffee or whatever else it might be. And if it's a good experience and you like it, right? And if it's a really horrible experience, you'll probably, if you're really young, you'll probably think, I don't like carrots. They taste funny. I don't like the texture, whatever it is. So I love pickles. I mean, Scottish pickles are great. I love big pickled onions. And I was eating a pickle and it was really strong and it takes the enamel off the teeth. And she was watching and I thought, well, I'll give her one, being stupid like that. And I handed her this pickle and she bit into it. They're about this big, right? She bit into it. And her face, you know, when you take a lemon, your face screws up. And her eyes, and she started, her tears were coming down her cheeks. I thought, oh God, I've put her off pickles for life. And when she'd finished chewing it, she went, good. And she loves pickles. So to this day, we share this common thing that we both love pickles. So everybody here is probably, not everybody, there's a large number of you here who like or dislike something and you don't know why. So I'm going to pick on Morgan first. Morgan, is there something you don't like to eat or drink?
Yeah, I don't like tomatoes.
Do you know why?
I don't think so.
So when you were 3, you probably had your first tomato, or 2, and it wasn't a good experience, and now you hate tomatoes. Could be. Right. Has Morgan went off anything yet, the little guy? Your little guy, I should say.
What was that?
Has he got something he doesn't like eating?
Cody, is there food you don't like?
Yeah,
What is it?
bananas.
Bananas.
Go figure. Right. Who else were you picking? Ethan, is there something you don't like eating?
I gotta say, green beans. I've never liked them.
Right. So probably a bad experience. Ripkin, you got anything?
I would have to say green beans as well.
Wow. Okay,
And
last person. Ray, what about you? Anything?
When I was little, I was a super picky eater, so I didn't like most things, but now I'll pretty much eat anything.
Okay, so you're a total contradiction to my theory then. That's fine. Okay, so what we're going to look at now is called a scatter plot. It's a way of representing information. Scatter plots are a lot easier to do, and I think probably a lot easier to understand. So imagine that you have a number line. And I'm going to start at 10, and it's going to go 11, 12, 13, 14, 15, 16. Should finish at 20 if I do this right. 17, 18, almost 19, 20. Suppose you give a class a quiz, 20 points, and everybody in the class got somewhere between 10 and 20. And you wanted to do a very quick visual way of representing that information, right? Now, I could just collect it in a frequency table and say 3 of you got 10 and 2 of you got 11 and so on, and that would work. But if you want a visual picture of it, you could do this. Now, do you notice that was pretty easy to do? Do you see it's basically just a dot? Each dot represents one person in the class that got that particular score. So if I had this in front of me, I could quite quickly just count 1, 2, 3, 4, 5, 6. 1, 2, 3. Yeah, 6 people in that class got 14 in the quiz, right? And can you see nobody got 19 and one person got full points and some 3 people over there got 10. So would you agree that's a very quick, easy way to see it, and it doesn't really involve a great deal of effort, but it's still quite useful, isn't it? It's very simple technique, but it's useful. If I was looking at this shape, I would probably, and this is not guarantee, but what I'm saying, if I can get my pens with the right caps on them, would you agree that this shape, with the exception of that funny little bump at the end, which we could argue about, is probably unimodal? I don't think that bump's tall enough to count as a bump, so I wouldn't call it bimodal. It's probably symmetric as well, roughly. I don't think there's any outliers, I agree. Definitely not any outliers. And you can use that information that's based on this and to come up with all sorts of cool things. So I am going to switch over here and show you a scatter plot of some real data. I believe it's real data. And this here is another display. This is a dot plot, scatter plot. This dot plot, the data values are displayed horizontal. A dot is then just telling you. The figures below shows the dot plot generated by Minitab, or the number of licensed drivers per 1,000 residents by state. Okay, so we'll assume that we're talking, although it doesn't mention it, I would make the assumption that if you had 1,000 residents, that state there, very roughly, has probably got about 820 of them have licenses. So for that reason alone, I'm going to assume this is adults that could have a license, right? You're not going to count 2-year-olds, right? So every single one of these dots represents how many people out of 1,000 actually have a driving license, right? So that dot there is about 800 and, I don't know, I'm trying to do a scale here, about 815-ish, 810, 820, that kind of ballpark.
Your screen isn't shared.
Ah, is it shared now?
Yeah, you're good now.
Okay, good. Now, back to what I was saying here. Do you see that basically is every state in America? I don't know enough about America, but let's go for extremes. I've got an idea, but it's only a guess. This guy over here is 570, 580, right? Roughly. There's a state in America where that's how many people actually have a driving license. I've got my idea. What state do you think it might be? See if you agree with me.
I think this is a ratio of land residents first off, but if my first guess would be that that's New York, saying as most people there don't drive.
That's what I was thinking. I think New York, i.e., I think to afford a parking spot, you'd have to be a millionaire. Just for starters. I would hate to think how much gasoline and taxes cost. So that would be my guess. Now, this one over here, I'm not so sure. I've got 2 different places I think it might be. And they're quite different states. Anybody want to have a guess? And that's really all it is. An intelligent guess. What state might have over 800 out of every 1,000 adults has a driving license? Pretty much almost everybody's got one that's wanting one.
I'd say probably Texas.
I wasn't thinking of that, but it makes sense. I was thinking California, a place just with tons of cars and people drive everywhere. But I guess Texas falls into that category as well.
My main thought process for Texas was just due to the sheer amount of land. Many people there have to buy vehicles to be able to travel from one town to another. It could take a whole day to walk to a place.
Right. What about where?
What about Alaska? Because that's really spread out too.
Yeah?
There's really.
That was going to be my second choice. I was thinking Alaska.
I was going to say Alaska's probably the one that would have the least amount because most of that area is desolate land and there's not a lot of functioning roads to have even a license in the first place.
Oh, that's an interesting thought. Yeah, but it's kind of cool that doesn't that generate kind of interesting questions like I wonder which state is which and why. And yeah, Texas I think is a good candidate for a lot, right? And California I was thinking maybe, but maybe I don't know California that well, but same kind of reasoning maybe.
Well, I also, with the whole Alaska thing, I'd like to point out that it doesn't necessarily say car licenses. And a vehicle that's more used up there is a snowmobile, but even then you need a license to be able to drive that legally. So,
Well, yeah,
depending
and you
on where
also
you're
have
from,
float planes. Surprisingly, I think the
also
largest
require
number of
licenses.
pilot licenses in Alaska, right? The state with the largest percentage of population is Alaska. A lot of people fly little planes. Kind of cool.
But the data says licensed drivers, so I don't think the drivers would also include plane licenses.
Oh,
That's a fair
boat
argument.
licenses.
But
that's a good argument. I agree. Right, so that's our questions. Let's look at their boring ones now. Our obvious ones, we'll call it. From this dot plot, how many states have 600 or fewer licenses? Well, if you look at 600, it's here, or fewer. Isn't it just one? At least that's all I can count.
one.
Yeah. Much more boring question, right? What percentage of the states out of 51, so thankfully they told us there's 51 of these, what percentage of the states seems to have close to 800 licenses? Okay, I do not like words close, because what you think is close and what I think is close may not be the same, right? So I'm going to pick, because I want to, all 5 of those. Now you might think, nah, only that one is close. Because in your definition, that's what close means. But if we pretend my definition is correct, and I'm not guaranteeing it is, as a percentage, won't that be 5 states divided by 51? Then you multiply by 100, and you will be looking at about 9.8%. Does that kind of question make sense? That from a dot plot, we could talk about how many are bigger than 800, how many are less than 600, what percentage are close to this. I think they went and finished with consider the intervals 550 to 650. So 550 to 650 is probably in this window here. 650 to 750 is that window. And 750 to 850 is the third one. And I think it's pretty obvious, isn't it? The middle window has by far the most. Now, if you are really interested in data and collecting data, taking something like that and then maybe comparing it against things like other countries in the world, right? Or you'd have to break them up differently. I know some countries break themselves into districts. What does Canada call their things? Provinces? Whatever. Do you know how you could compare different countries in the world and get some kind of interesting thing? Oh, cool. You may or may not have seen this funny looking guy. You see it? It says use salt. I think there are a couple of examples at least up here if I scroll to them. You know, I won't find one that I'm looking for it. I know there's one up here. Keep going, you'll find it. No? Okay, I can't. My memory's bad. Okay, let's show you how salt works. S-A-L-T. This data, if you click on use salt, oh, darn it. Can you see Cengage Learning Salt in the screen? Can you see that now? Okay. When I clicked on it, this is what happened. It took the data from this question and it transferred to this thing called SALT, right? It's an analysis and learning tool. If you then hit graphs and charts, you can hit dot plot and you can select variable, boom. And guess what? It does the dot plot for you. Can you see that? Now, it's worth it, I guess. Or you could just do it by hand. And if you did it whatever way you decide. One of these pictures would be the right one, and you just pick it. So here is a set of data, do a dot plot. And then look at your dot plot and say, my dot plot looks like this guy, or my dot plot looks like that guy. It'll look like one of them, and that's one you pick. Right, here's another one. This is tumor data. We'll collect it. Transferring the data, just done so. If I go to charts and graphs and ask it to do a dot plot again, and pick the variable time. Right, now this is a dot plot for how long it takes a tumour to reoccur after it's been killed off, the original one has been killed off with chemotherapy. When I look at this data, I do not see a great deal of pattern. Would you agree it's pretty much uniform? Just from left to right, it can. So what does that tell me? It tells me then that if you get a tumour, it could happen like next month, which happened to that poor soul, right? Or it could take 4 years, which happened to those two people. And different tumours, so in this particular case, this tumour could happen anytime. So if you're in chemotherapy, based on what we've just seen here, wouldn't it be a good medical thing to get a checkup every year for at least 4 years? Because sometimes these tumours take 4 years or 5 years if you want to be safe, right? Until you get that. I'll share a story with you. True story about me. Me and my wife were in Scotland, and I was driving along, and I wasn't seeing too well, and I thought, well, I'll need to get my prescription changed. No, I wasn't seeing, wasn't being able to read carefully, and I didn't think anything else of it. You know, I'll wait till I get back home to America and I'll get a new prescription. But it got to the point where I said, oh, to heck, I'll just get my glasses in Scotland. So I went into an optician's there, you know, the kind of thing you get, and they gave me my test, and they gave me one of these, don't know if you've had it, do you get the one where they do the little flashing lights and you hit a button when you see them? You ever seen that? Anyway, they gave me that test, and the woman looked at the results, and she went and said, come back tomorrow, I want you to do that test again. So I thought, oh, I wonder what she wants. So I went back and I did the test, and I got the same result. And she wasn't happy because there was something wrong with my visual. I was losing peripheral vision all the way around. And so she went and said, when you get back home, talk to your doctor right away. And I went to, when I got back home, I phoned up my doctor and said, look, I got this test and my peripheral vision isn't there anymore. It's disappearing on me. And he said, come in tomorrow. So he was obviously concerned as well. And I went in, and he'd done the same test and got the same result. So he said, oh, okay, you're going to have to do an MRI. And I got one. And the bottom line is that I had a tumour. I had what's called a pituitary gland tumour in my brain. And it was growing big, and it was pushing on my optic nerve. And that's how I was getting the visual issues. And so the first treatment is they give you a pill. And for some versions of this tumour, the pill basically kills the tumour, or it shrinks it to nothing. But that didn't work for me. So I had to go in, and I got keyhole surgery. If you're into medical, you'll love this. Some of you are going, ugh. They stick a hole through your nose and another hole through your upper palate, and they stick in these little, do you see the keyhole, little gizmos? One's a light, and the other one was, I was totally out. But the other one basically had like a rotating blade on it, and they just sawed it away and sucked up the blood in the guts. And that's how they get rid of my tumour. And for the same reason that this table is here, I had to get an MRI scan every year after that to make sure that the tumour hadn't grown back, because in about 50% of the cases they do. And I got one every year for 3 years, and then it went to one every 2 years for 2 more years. And now it's one every 3 years. So I get an MRI every 3 years now. And the doctor did a great job, got rid of it. He told me what isn't the depressing thing, but when I was looking at my neurosurgeon, the one who did the operation, he was saying, you're lucky you didn't have it 20 years ago, because you'd be dead. Because they didn't have the keyhole surgery, and the mortality rate was so high that most of the time they didn't even perform the operation. It was basically a death sentence. So I got lucky to have a tumour at the right time when they had, you know, all this new gizmo stuff. Unless I'd caught it in Britain, because if I had got it in Britain, I would have been dead. Because socialised medicine means that I would have to have waited in a queue for so long that I would have been dead before I got it, because I'm too old. 20-year-olds would get that before I would. Right, I would, right? So, be careful what you wish for. Just telling you. Okay, that was cool. Scatter plot. Nice stuff. Histogram, covered that. We are about finished that one, so that gives me a chance now to close this off, and we will look at what is in store for us in the next section. And it gives me a chance to talk about some of you. I'm glad to say not many of you got an email from me, because WebAssign sends me out a list of people who haven't been doing their homework assignments. And so I send you out an email saying you haven't done your homework assignments. So will you make sure that you get them done by Sunday, midnight? That's chapters 1 and 2. We are now going to look at how you can, how you deal with data that's qualitative. We just finished doing quantitative, right? What can you do with quantitative stuff? Well, you can do dot plots, you can do histograms, you can do frequency tables, you can do cumulative frequency tables, quite a lot of cool stuff. Qualitative data, right. Well, let's look at the two main kinds and show you the differences between the two. The first one is going to be nominal. And the second one is called ordinal. And this one is non-numeric and no real order. And the second one is, pardon me, ordinal. It's also non-numeric, but it has some kind of order, some natural order. First kind of diagram, very simple diagram. I don't know, you could have even been 6 the first time you've seen it. Have you ever? Yes.
So do the other ones not exist for qualitative because it's not numbers?
Correct.
Okay.
Yeah, nominal is for non-numbers, right? Red, blue, green. Ordinal is for non-numbers typically, but there's an order to it, you know, like sophomore, junior, senior, right? There's some kind of natural order, even if the thing you're counting is not a number, right? And we're going to look at the first kind of chart called the bar chart. So let's do a nominal. Let's suppose, I'll pick some simple. Let's suppose you went and asked some 5-year-old kids what their favorite color is. And to make life easy, the colors that came back. I think I'll do one more. I'm running short of obvious colors. Somebody give me a color to finish off with. Say again?
Green.
Green will do it, right? Okay. And you have frequency. Now, in a very similar way, can you have frequency tables of nominal data? Basically, you just add up how many. And let's suppose that's 3, that's 7, that's 5, that's 2. There. And this was 10, 20. So this was a total of 20 kids. And you said, what's your favorite color, John or Maeve or whatever the name is? And this is what you got. That can then generate a bar chart. So what are the main features with the bar chart? Well, it looks very like a histogram. Along the bottom, you're going to choose color, and vertically, you typically would choose what we call frequency, but not always. Oh, I guess I need a scale here. 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, here we go. And you leave a space typically, and you draw a rectangle the same width, and you draw it 3 high, and you call it red. Then you leave a space, and you do another rectangle, and you do it blue, and you go up to, I just noticed I screwed up there, but can you pretend I didn't? And this is blue. Then you leave a gap, and you do yellow, I'll just call it Y, and that's up to 5. And then you do a gap, and you do pink, and that just gets up to 2, call it P. And then right at the end, you've got green. And you go up to 3. And you probably should have a heading, which is, in this case, children's favourite colour. Agreed? Are you all remembering to spell properly? So colour and favourite and whatever else, don't they have a U in them? Joshua, colour has a unit, agreed?
Yes.
Morgan?
No.
You're not going there, okay. Children, very early age in high school and junior and before that as well, don't you very often get to do simple things like this? These are very straightforward, but they're visually very appealing. If you really go fancy, don't they make this one red in colour, this one blue in colour, and this one green in colour, and you can do a whole load of cool stuff. But there's nothing really too difficult about that. Technically speaking, there is a lot of things you can do to this that you can't do with the other ones. Couldn't I rearrange the order of these colours to any order I like? I mean, there's no reason why red was first and pink was, you know, towards the end. Couldn't I have made pink first, green, yellow, red, and technically speaking, that would be the exact same information. That's why colours are nominal, right? There's nothing in there. For that reason, you cannot look at these and describe them the way you typically would maybe describe histograms. You cannot say, for instance, it's unimodal, or it's skewed left, or it's skewed right. Do you know all those terms that we used when it was histograms? They don't make sense, because couldn't I rearrange this data to have it skewed left, skewed right, unimodal? Couldn't I? I mean, I could do it any order I like and make it look that way. So none of those descriptions should ever be used. There's not that much more you can get out of this chart, except the obvious things like blue is the most, the favourite colour of children, at least in this group, and pink was the least favourite colour. You can also take this table and expand it to have only one more column. And it's not going to be cumulative frequency, because for bar graphs and for this type of data, it makes no sense to do that. What do you think the only other thing you could do with this data is? What do you think the last column is going to be? You can also find the relative frequency. So 3 out of 20 comes out as 0.15. 7 out of 20 becomes 0.35. 5 out of 20 is 0.25. 2 out of 20 is 0.1, and finishing with 0.15. You sometimes find that these frequency tables can also have relative frequencies attached to it. And at the same time, couldn't you also turn these guys into percentages? Because sometimes relative frequencies are given as percentages. This particular one that I've done, didn't I use the frequencies to generate the vertical column? If I wanted to do this same chart, but relative frequencies, wouldn't I have to change this vertical scale to be what numbers like 0.05, 0.1, 0.15, right? Change that. If I wanted to do it as percentages, wouldn't I have to change the scale again? So let's pretend that I was going to do it as a relative frequency. And I was going to use the percentages. So I might go 5, 10, 15, 20, 25, 30, 35%. Well, the first guy is red again, but now it's 15%, so it goes here. The next guy is blue, and it's 35%, so it goes away up the top. The next one was yellow, and it goes 25%, which is about here. And pink is the next one, that goes 10%, which is about here. And lastly, green is 15%, and it goes here. If you look at these two side by side, aren't they basically the same picture? You know, they go up and down relative to each other the same amount. So the only difference between this particular bar chart and this bar chart is that the vertical scale is the raw data, the frequencies, and here the vertical scale is the relative frequency. That makes sense? Right. Now I'm trying to think of why anybody'd want to do this. So here's a made up reason. Can you imagine you were making toys for children and you wanted to know what kind of colors it would be best to make your toys so that the children would buy them, right? They would want them. Wouldn't you probably want to choose colors that children like? So make your toys like blue and yellow, and not maybe make your toys pink, unless it was a doll, I guess, right? So you can imagine people who make things are asking questions about, you know, things like that, and then they can choose to use that information to help them in their business world. So are we cool with bar charts and how you create them from nominal data? The main features are put it in any order you like, spaces between them, and label them. Well, let's look at ordinal data then. Now that's non-numeric, but there is an order to it, right? So let's try and figure out something I haven't done with an order to it. Okay, we're going to have, what are we going to have here? I get up. I need a different piece of paper. We're going to do strongly agree. We're going to do agree. We'll say you've got no opinion in the matter, you know, you don't care, 50-50, that kind of person. You're going to be a disagree, and then you strongly disagree. Right? So this is a very common Likert scale, L-I-K-A-R-T, right? There are 5 choices. Sometimes they're called in a scale of 1 to 5. And sometimes you have to read it carefully, because sometimes 1 is strongly agree, down to 5 strongly disagree, but sometimes they switch it round. You know, 1 is you strongly disagree and 5 is you strongly agree, right? And so I need to do a question here, and I am going to get you lot to take part, at least those who want to, right? So do you know that little hand guy, this fella here, where you go thumbs up? So we'll do it that way, and I'll try and keep it. Now I have to try and find a question that you are willing to have an opinion on, and we'll try and collect some real data. So I'm going to, okay, what shall we choose? Okay, if this one doesn't work, then somebody can give me a question. I think sci-fi movies are the best kind of movie to watch. Right, so that's a statement. I think science fiction movies of all the genres, right, are the best movies to watch, right? Okay. How many strongly agree with that statement? One. I'm counting my votes, so there's two of you. Is that it? There's two of us. Okay. How many just agree with it? They're not strongly agreeing with it, but they think, yeah, okay, could be right. 1, 2, 3, 4. I think you got 4. 5, 6. Oh, you come in late. Okay. If I miscounted, it's about 6, right? How many have no opinion on that at all? They couldn't care less one way or the other. Hannah, anybody got that opinion? Ryan's got it. If he wants to share, so is she. No, that's better. Looks like it's 6 again, roughly. We're on to how many disagree with me? They have a different genre, a different kind of movie. Morgan definitely, Gabriella, Ethan likes to watch different things. Oh, that's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 11. And how many are strongly disagreeing with that then? It's almost like, I hate those movies. That's the worst movie I'd ever go and watch. Okay, we got 2 of you. That's an example of me using a Likert scale, right? Now, would you agree that this scale has a kind of natural order to it, right? You can strongly agree to strongly disagree. You can switch it and start with strongly disagree and finish with strongly agree. That's equally correct, right? But it does have a natural order to it. So if you were going to create your bar chart, you would have along here something like opinion of sci-fi and
We can't
vertical.
see it.
Oh, sorry. So we have opinion of sci-fi, and then we have frequency. And you have strongly agree, which is what I'm doing first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11. So strongly agree. 2. How many agree? Oh, a little bit more, 6. Right there. And next one's exactly the same, 6. So that's no opinion. Then we have disagree, which climbs all the way up to 11. And then finally, we have strongly disagree, and that climbs up to 2. There's not an awful lot of difference, isn't there, between the bar chart of this guy and the bar chart of that guy? The main difference is not the structure. They look very similar. Isn't it that there is a natural order to put them in? It wouldn't be very helpful to jumble these up randomly, because then it wouldn't really be as clear as it could be. The fact that there are 2 correct orders to this, couldn't have rearranged the table like, and it still would have been valid, right? It's okay to have 2 directions, as long as you've got a direction. And you could go through all of this. While we're at it, I love science fiction, as you have guessed from my question. My wife actually does, but she's a little bit more selective than me. But I have been to girl flick movies with her, because when we do movie nights, when human beings were allowed to do movie nights, we'd go out to a girl flick movie. And so I'll share with you, this is every girl flick movie in the world, including Hallmark movies. You ready for it? This is the story. There is a guy and a girl that you know within the first 5 minutes are going to get together, right? At the beginning, they don't get on well, right? They fall out with each other. She doesn't like him. He doesn't like her. Whatever the reason is, there's some reason they don't get on together. As the movie progresses, don't they become closer and closer together until they become a couple? And then 10 to 20 minutes before the end, doesn't something bad happens that makes them want to separate again? The old girlfriend comes on the scene and and the other one gets jealous, whatever it is. Oh, I've just found out you're going to sell my dad's company because you're a lawyer and you didn't tell me you were a lawyer. You know that, whatever it is. And then 5 minutes before the end, doesn't everything come back together again and they all sort it out and they live happily ever after? Is that a girl flick movie? Morgan, you are nodding like you know exactly that's a girl flick movie. So why on earth do you watch them if you know how it's going to end? I know why I'm picking on Morgan today. Poor thing. Right.
I watched them because I like that plot. Like, I like that I already know what's gonna happen.
You don't like nasty shocks. So if a girl flick movie ended up with him running away with some other actress that you didn't even know was going to be in the plot until the last 5 minutes, and the other one committing suicide, you don't want to watch that movie because it's sad and depressing and not very nice. So you want to say, oh, I bet you so-and-so is going to hook up with so-and-so. Avery, you're looking like you've never... if you get married, young man, trust me, you are going to have to suffer girl flick movies.
No. I was kind of grimacing because I'm like, the exact last scenario you're describing where it's all tragedy, those are my favorite kind of films, is the ones where I'm sitting here guessing the twists. But my family hates watching movies with me particularly because I'm really bad at, I can guess everything that's going to happen, even if it's like a really, really crazy twist. And I'm like, there's the foreshadowing, there's this. And they're like, dude, it's no fun to watch movies with you. And I'm like, I know, this is why I watch everything on my own.
I do that.
But I can understand it. My wife loves Christmas movies for the same reason. She's a great Christmas movie fanatic. And sometimes they do a girl flick Christmas movie merge. And the only difference is that in Christmas movies, there's Christmas involved in some way. That's it.
Yeah, I think I've seen one that was literally called the Christmas Prince, and it was a Hallmark movie. So.
Oh, it wouldn't surprise me. My wife, this is telling you this is true. My wife showed me a list of all the Christmas movies that are going to be in Hallmark. And she's sent it to her sister who's going to be staying over Christmas. And what their job is to do is to go through the list and put a cross on the ones they've seen so that they can only tape and watch the ones that they haven't seen. If you gave me that list, I just put a cross in all of them, because even if I haven't seen it, I probably have, because I know how it's going to end. But that's
feel like as guys though, like there's definitely shows that repeat a lot, like CSI or whatever. It's just the same thing every week. But Hallmark movies are painful. They really are.
Well, the good news is that it's kind of cool to be with your wife, because
I mean,
just because I'm with her, it's cool.
To be fair, in this scenario, one of my favorite movie series is John Wick, and it's like, you know what's going to happen during 1, 2, and 3 once you've seen one. It's not hard to guess, but it's still fun because of the actual experience and the emotional roller coaster ride, which may be a fair amount of why people enjoy those Hallmark romance movies. Always fun.
I'm giving you a hard time, but I think it's healthy to just have nice movies where nobody gets killed and everything finishes happy, and that's cool.
Look, I like the Trolls movies too, okay?
Okay. I can't fault you with that. I was going to say, I don't know if I can't remember the series, but it goes something like London has fallen, Olympus has fallen, and some other place has fallen. Do you know that sequence of 3 movies? And in those movies, lots of people get shot and killed and so on. But there's one thing you know, that the main CIA guy is going to kill all the baddies before the end. So that's a kind of different version of, you know, how a movie's going to finish. Okay, well, let's get to really, for the short time that we've got left, why don't you, while I'm getting set up, vote, tell me hi so that I know you're here, and that'll give me a few moments to look at some of the questions from the homework so we can get an idea of what's expected of you. Okay. You all voted? You all said hi? That's me got attendance. And let's just, what we got left, about 10 minutes. Okay. I think I'm on this one. Okay, here we have a story with some data. What they're looking at here is some information that's been given in the form of a bar chart. Now, have you noticed that their gaps are a little bit smaller than mine? I just choose big gaps for emphasis, no other reason, right? As long as there's a noticeable gap, it's called a bar chart, right? So we're looking at this one, and it's asking a question that a lot of you should ask themselves this. It is costly in both time and money to go to college, right? Now, obviously you have to pay for college, student loans. Secondly, while you're at college, you're not working, right? You could be doing a 40-hour job instead of a 20-hour job, right? So that is definitely a negative to coming to college. So does it pay off? Well, according to the Bureau of Census, the answer is yes. So this is the average annual income in thousands of dollars of households headed by a person with a stated educational level as follows. So basically, whatever the family unit is, it could be 2 guys, it could be 2 females, right? Male and female, married or not, doesn't matter, right? It's a household. That's what the government call a household, right? A unit with very often children. And what you can see here is 24.4, 24 and a bit thousand if you only got to 9th grade. So if you quit school, basically a dropout, the average is 24 and a bit thousand. Now, can you find a rock star that's making $1 million a month who did that? Sure. So for every single rock star that you could find that, can't you find 50,000 other people who are working, you know, $12 an hour jobs? So this is an average. Next one up after that is that if you at least graduated from high school, 40-odd thousand is the average that you'll make once you become established in your career. I think I'm out of sync here. Let's use, yes I am. 82 for those with a bachelor degree, that's pretty good. Right, now you won't get 82 the minute you leave university. We're talking about, you know, typically you don't reach your optimum until you've reached your career, which is about 10 years. Takes you about 10 years in most jobs to do that. But 80,000 is not bad. 100,000 for a master's degree. I know I'm in the wrong job. And 121 if you get a doctorate's degree. And then there's a whole load of bar charts here, and they basically give all that information and you just plug it in, and one of these pictures is the right one. I'm pretty sure it's not that one, right? Because that means you make less money the higher your education level is. This one seems to go up and down, and from what I can see in the data, that doesn't match. It looks to me like it's this one, isn't it? When you see it written like that, it's a little bit clearer that you can see that it's almost like linear going upwards. ninth grade, high school, associate's degree, bachelor's, master's, and doctors. So I don't know where in the food chain you intend to be, but right now you're definitely in the associate's one. And if you look at the difference between here and here, that's the difference in 1 year's salary. So if you work for 20 years, can you imagine timesing that by 20, in which case that would add up to a fair chunk of money. And that would certainly pay for your lost earnings and student loans. Well, that is assuming that you get a degree in a useful career. I wouldn't probably go to university and get a degree in contemporary music and dance, because you probably won't get a really good job at the end of that. On the other hand, if you do computer science, you'll probably get a job with Amazon within the first bloody week and make more money than it took me 20 years to get to. You can tell I'm jealous. One of the reasons I slag all my fourth year, my Calc 4 students, because a lot of them are engineers, is because I am jealous. Because a lot of engineers will make more money than I do, probably after a couple of years of graduation. So if any of you are in that business, another place, we could probably make a lot of money. But then again, you don't get as much fun as me. Maybe. Well, here are just a whole load of particular diagrams. Right, I think I've done that. Yeah. So, where are we off to? Have I got time? Yes, we do. Okay. The last few minutes, I'm going to very quickly tell you some other shapes, other diagrams that you can get from data. Have you ever seen guys that look like this? Red,
Pie
blue,
chart, right.
green, yellow, pink, right? Pie chart.
Generally used for percentages.
You can use them for percentage. You can actually use them for any of the data that we talked about, but you can use this for any kind of ordinal or nominal data. So you can imagine this piece of the pie is the kids that like blue, and this piece is red, and this is purple, and this is yellow, and this is green. And they are horrendously difficult to draw correctly. What you do is, let's pretend, just for argument's sake, that 20% of the kids like blue, right? So I did a different survey. What you then have to do is you have to find 20% of a complete circle, which is 360 degrees. And 20% of 360 degrees, I believe, is 72 degrees. And then you use this funny little thing called a protractor. Ever seen that damn thing? Piece of plastic. And you place it on here and you measure 72 degrees worth, and you draw the other line. It is as painful as anything to draw accurately. Secondly, when you look at these pictures, can't you really only tell who's big and who's small? You can't really tell what the numbers are. But it does happen. Have you ever seen a chart that looked like this? So let's suppose we asked kids only what colour they liked, and we only gave them 3 colours to pick from. So from these 3 colours, which one do you like the best, right? So you're not giving them infinite choices. And this is what the data looked like. Now, the ones that are shaded are girls, and the ones that are not shaded are boys. So what you do with this particular thing is that you kind of think of it being built on top of each other. So for instance, for red, 5 girls. From 5 to 15, whoops. So that's girls. For boys, Can you see it's the other 10? 5 girls, and then on top of that, 10 boys. So it's not 15 boys like that colour. The white rectangle above it is the boys' score. So don't you have to read this number, read that number, and do a quick subtraction. Now, if this was true, and it's totally sexist and probably also totally wrong, wouldn't you be able to say things like, little girls love pink a lot more than little boys love pink? And little boys, little girls don't like blue, and little boys like blue a lot more.